We will now study the modern electron theory of magnetism, which explains magnetic properties of magnetic materials.
You must have wondered why a molecule of a magnetic substance like iron behaves as a magnet. We know that a molecule consists of two or more atoms. Every atom has electrons moving in its orbits around its nucleus. An electron carries a negative electric charge. The moving electrons in an orbit create an electric current in the orbit. This electric current produces a magnetic field. Also, the spinning motion of an electron produces a magnetic moment. Thus, the net magnetic moment due to a molecule is not zero in case of a magnetic substance. In case of a non-magnetic substance like wood, the net magnetic moment due to a molecule is zero.
We will now learn about magnetic properties. The most important magnetic properties are magnetic permeability and magnetic susceptibility. We have already learnt about magnetic permeability. Magnetic susceptibility is related to the ability of a material to get magnetized when placed in an external magnetic field. Such ability is called magnetization, and it is measured by a quantity called intensity of magnetization, represented by I.
In general, when a substance is placed in a magnetic field, the atomic magnets tend to align themselves parallel to the direction of the applied field. Therefore, the substance as a whole acquires certain magnetic moment. Intensity of magnetization. The magnetic moment acquired by a substance per unit volume is defined as intensity of magnetization I. The unit of intensity of magnetization is ampere per meter.
The ease with which certain substances allow themselves to be magnetized is called magnetic susceptibility.
When two different substances are placed in the same magnetic field, the amount of magnetization produced in them need not be the same. The difference is due to different values for the property, that is, magnetic susceptibility. Magnetic susceptibility is defined as the ratio of the intensity of the magnetization I and the intensity of the applied magnetic field H. Thus, magnetic susceptibility is equal to I by H, which is equation 22. Note that magnetic susceptibility is a constant and does not have any units for a given substance.
Retentivity. It is a property exhibited by certain strong magnetic substances. When a magnetic substance like iron in the form of a rod is placed in an external magnetic field, the substance is magnetized. It acquires certain intensity of magnetization I. What happens to this magnetization if this magnetic field is switched off? That is, H is equals to 0. It is observed in certain substances that I does not become 0, even though H is equals to 0. That is, certain amounts of I is left or retained in the specimen as a residue. This property is called retentivity. Retentivity of a magnetic material is a property by virtue of which it retains certain amount of intensity of magnetization even after the removal of the applied magnetic field. Let us now learn about magnetic classification of materials. Magnetic materials can be grouped into three classes based on their important magnetic properties. The three classes are diamagnetic materials, paramagnetic materials, and ferromagnetic materials. In atoms of certain materials like air, water, or bismuth, the orientation of electron orbits and the axis of their spin are such that the resultant magnetic moment of any atom is zero. Such substances are called diamagnetic in nature. Diamagnetic substances are those in which the resultant magnetic moment of the individual atom is zero.
When a specimen of a diamagnetic substance is brought near a magnetic pole of a bar magnet, it develops a similar or like pole, and it comes to rest in a direction at right angles. Therefore, it is repelled. When a diamagnetic substance is suspended freely in an external magnetic field, it comes to rest in a direction at right angles to the field direction. The relative permeability μr of a diamagnetic substance is approximately equal to 1 or less than 1. Mu is less than or equal to 1. The magnetic susceptibility of diamagnetic substance is small and negative. Some more examples of diamagnetic substances are gold, alcohol, mercury, and hydrogen. Strictly speaking, diamagnetism is a universal property. When other magnetic properties dominate, the diamagnetism is not observed.
Paramagnetic materials. In certain substances like oxygen or solutions of salts of nickel and manganese, the orientation of electron orbits and axes of their spins are such that the resultant magnetic moment of any atom in them is not zero. Generally, the atoms with unpaired electrons acquire resultant magnetic moment. Such substances are called paramagnetic in nature. Paramagnetic substances are those in which the resultant magnetic moment of the individual atom is not zero.
When a specimen of a paramagnetic substance is brought near a magnetic pole of a bar magnet, it develops an opposite or unlike pole and therefore is attracted. When it is suspended freely in a magnetic field, it is attracted towards stronger field and tends to align itself along the direction of the magnetic field. The relative permeability μr of a paramagnetic substance is slightly greater than 1. That is, μr is greater than 1. The magnetic susceptibility of a paramagnetic substance is small and positive. Aluminium, platinum, and chromium are some examples of paramagnetic substances.
Ferromagnetic materials. In 5 elements, iron, cobalt, nickel, gadolinium, and dysprosium, and a large number of their alloys, a special effect occurs. The atoms of these elements have resultant magnetic moment because of unpaired electrons, like in paramagnetic substances. When a solid specimen is formed out of atoms of any of these 5 elements, the special effects present in them permits the specimen to achieve a high degree of magnetic alignment. Such substances are called ferromagnetic in nature.
Ferromagnetic substances are those in which the resultant magnetic moments of individual atoms align themselves in parallel locally because of a special effect present in them, giving rise to spontaneous magnetization. In a ferromagnetic substance like an iron rod, there is always some amount of intensity of magnetization even though the applied magnetic field is zero. This inherent or spontaneous magnetization is due to a special effect called exchange coupling between the adjacent atoms in the solid. The magnetism that we deal with in our daily life is actually an important branch of subject, ferromagnetism. The ferromagnetic substances are strongly attracted by a magnet. They align themselves easily in the direction of the applied magnetic field.
The relative permeability mu r of a ferromagnetic substance is very high, that is, mu r is greater than 1. Similarly, magnetic susceptibility of a ferromagnetic substance is very large and positive. Therefore, they can be easily magnetized and made into magnets. In spite of these strong magnetic properties, a ferromagnetic specimen like iron is not a magnet by itself. You must wonder why. The answer lies in the domain theory of ferromagnetic substance. In a ferromagnetic substance, the adjacent atomic magnetic dipoles are parallel, but they are parallel over only a small region called domain in a specimen.
Domain in a ferromagnetic substance is a small local region in which all the magnetic dipoles align parallel to each other, giving rise to certain magnetization within the domain. In a ferromagnetic substance, a large number of domains occur. The direction of magnetization within a domain is different from that in the adjacent domain. These boundary lines indicate that the domains and the arrows within domains indicate total magnetization. You will notice that the arrows in the different domains point along different directions. As a result, the resultant magnetization of the specimen as a whole is almost zero. That is why an iron rod is not a magnet by itself. However, when an iron rod is magnetized, the domains expand in space such that all the arrows align themselves parallel to each other in a single direction. For an ideal magnet, there would be a single domain with all the molecular magnets pointing in one direction. Thus, the specimen acquires north and south poles and becomes a magnet. When we demagnetize a ferromagnetic substance, the original domains do not form immediately. Therefore, a certain amount of magnetization is still retained. This residual magnetization observed in ferromagnetic substances is the property already defined as retentivity.
Let us again recapture what we've just learnt. The magnetic moment acquired by a substance per unit volume is defined as the intensity of magnetization. Magnetic susceptibility of a substance is defined as the ratio of intensity of magnetization I and the intensity of applied magnetic field H. Retentivity of a magnetic material is the property by virtue of which it retains certain amounts of the magnetization when the applied magnetic field is made zero. All materials can be classified into diamagnetic, paramagnetic or ferromagnetic substances. Diamagnetic substances are those in which the resultant magnetic moment of the individual atom is zero. Paramagnetic substances are those in which the resultant magnetic moment of the individual atom is not zero. And ferromagnetic substances are those in which the resultant magnetic moment of individual atoms align themselves in parallel locally because of a special effect in them, giving rise to spontaneous magnetization. The relative permeability mu r of a diamagnetic substance is approximately equal to 1. For a paramagnetic substance, it is more than 1, while for a ferromagnetic substance, it is very high. Well, I hope you learned something interesting in today's session on magnetism. That's it for now. See you in the next session. Bye.